Here in Lecture 25,
we're going to take a look at the issue of who owns pointers to dynamically allocated objects, and therefore who is responsible, or which part of your code is responsible for properly deleting these dynamically allocated objects. I'd like to review what we looked at back in
Lecture 19,
about the classes that we were using for arithmetic expressions. We had term, constant, binary op, plus, and term was our base class, which has these two pure virtual functions, toString and toValue, which therefore need to be overridden in the higher level classes. Constant was one of the higher level classes derived from term that has specific implementations of toString and toValue. Binary op is still an abstract class. It is a base class used for things like plus, times, minus, divides. And what binary op does is to take the two operands, the left and right operands, and keep the pointers to those things in these left and right pointers to terms, data members within the binary op object. Now, at this point, we had the binary op object become the owner of these pointers, so that when the binary op object was destroyed, the binary op operator destructor did the deletes of the left and right side. And by having the binary op be the owner of these pointers, this enabled us to build an arithmetic expression using binary op operators to combine together the various terms in our expression, so that we only had to do a delete of the pointer to the topmost binary op. In this case, we did a delete of the second plus operator, and that took care recursively of deleting the other plus operator as well as the three constant objects in the expression. This is fine, but we discovered that we had trouble when we tried to add one term twice. That is, we defined a variable class in the homework, and if we tried to make use of the same variable two times, then when we deleted the top level term in our arithmetic expression, that ends up causing the variable to be deleted twice. The first time is fine, but the second time causes a crash. So this is a very common problem and gets us to an important question, which is, in your application, who or what owns the pointers to the dynamically allocated objects, and therefore who or what is responsible for deleting those objects when you're no longer using them?
one good solution to this is to use a shared pointer.
Let's have each object be its own owner. So each object that is allocated is responsible for cleaning itself up. And this can be done using a standard so-called smart pointer type, specifically the shared pointer. The cool thing about shared pointers to objects is that when a shared pointer to an object goes out of scope, then the object that that shared pointer is pointing to is automatically going to be deleted. We don't have to worry about deleting objects ourselves. We don't have to worry about having a base class clear function that will do that for us. If we use shared pointers correctly, this will simply happen. Now, to use shared pointer, we have to include a standard header called memory. So here, starting on slide 14, is our code making use of shared pointers. We include memory. Our term base class is back to being the very simple thing that it was initially. It has a constructor that does nothing, a virtual destructor that does nothing, and two pure virtual functions, toString and toValue, so that term is an abstract class. The definition of the constant class and of its toString and toValue functions is not changed at all. In binary op, we do have to make a change so that we no longer have ordinary term pointers to keep track of the left and right children of the binary operator. Now we're using shared pointers to terms for the left and right values. Okay, so we simply replace term star with shared pointer and then term in angle brackets to indicate that we're using smart pointers to these left and right sides. The destructor for binary op now has nothing to do because the shared pointers will clean up after themselves. Plus, shown here on slide 17, is a kind of binary op. We need to change the interface to the plus constructor to receive two shared pointers to term for the left and right operands of the plus. And these shared pointers are then simply passed down to the binary op base class constructor. A shared pointer can be used just like an ordinary pointer, so even though left is now a shared pointer to term rather than a term star, we can still say left arrow 2 string and likewise right arrow 2 string. We can use the same notation with the same expected functionality for shared pointers that we do with ordinary pointers. On slide 18 is our revised application using shared pointers. So instead of having C1 be an ordinary pointer to constant, we now say that C1 is a shared pointer to constant, initialized with the address of this newly allocated constant. Likewise, C2 is a shared pointer to constant, C3 is a shared pointer to constant, P1 is a shared pointer to plus, P2 is a shared pointer to plus, and these shared pointers all behave as ordinary pointers do, so that I can call P2 arrow string and P2 arrow 2 value. However, notice that at the bottom of main, I have no delete statements, I have no clear statement, because shared pointers, although they behave like pointers, they are in fact objects, and when they go out of scope, the destructors for these objects are automatically called, just as the destructor for any object that goes out of scope is called. And the destructor for the shared pointer will automatically do a delete of whatever dynamically allocated storage is being pointed to. So this is very nice because now we can have multiple uses of any term. We can use the constant C1 multiple times. We could declare a variable and use that multiple times, and so forth. And we don't have to delete anything. We just allow the shared pointer to clean up after itself.
The syntax is a little bit messy. Now, we can both clean up the syntax and improve some readability as well as efficiency by instead of writing out this detailed declaration, shared pointer constant, for our variable C1 and C2 and C3, and then explicitly invoking new to create a new constant object for that shared pointer to contain the address of, we can avoid using new by instead using mix shared with the data type of the thing for which we want to create a shared pointer. Here we can specify our initial value or initial values in the case of plus, and that will create for us a shared pointer to constant, or a shared pointer to plus in the case of make shared plus. It also eliminates the need for us to use new explicitly, which is pleasing, I guess, because in all conditions that we've talked about in the past, using new explicitly required us to use delete explicitly. Here we're sort of finessing things by calling make shared, which is hiding the actual use of new. The other thing is that we don't have to explicitly declare the data types of our variables. We can simply use auto as a shorthand, because make shared will produce for us a shared pointer to the correct type of thing, and the compiler can deduce what the data types of those variables are. Okay, so that takes care of that.